Hi everyone. I thought I would record a quick video talking through some of my notes that are a review from Equilibrium from Advanced Chem 1. This is totally optional, but if you're reading some of the notes, this might be helpful. You can also find almost all this information in your textbook, so if there are any sections there that you need to read, that could also be useful. So you're going to take this pretest. I want you to do it without your notes. It's going to give you a good idea of what you remember and what you forgot. There is an answer key that I want you to check. I think it is all correct. And then after that, I want you to read through the unit topics. This is what was given in Advanced Chem 1 again, and kind of rank yourself on how you feel about these topics. So some of this we will talk about in class, but not too much, because I want you to know it ahead of time. Reaction rates we've talked about. This is the speed that the reaction goes in. Something important to know is that the reaction never stops. It just reaches what is called a dynamic equilibrium, which means that the forward rate and the reverse rate are the same. So rate of the forward reaction, rate of the reverse reaction are equal. However, the concentrations do not have to be the same. Concentration of the products do not have to equal concentration of the rate. All that has to be true is that concentration of the products does not have to equal concentration of the reactants. All that has to be true is that your forward rate and your reverse rate are equal. Okay. This often depends on how fast the particles collide, which we learned in our previous chapter. Okay, so this is kind of similar to the how to get a date speed of the reaction. Things you can control are the concentration of the reactants, pressure, temperature, physical state of the reactants. What we're talking about here is the surface area of a solid. You could add a catalyst, you could add light. And there are good explanations in each of these sections for how this speeds up the reaction. So you want to read through the paragraphs and make sure you understand that material. Okay, so we're going to be talking about reversible reactions here, which are reactions that go backwards and forwards. Important to know, concentration of the compounds does not have to be the same. All that has to be true is that the rates are equal, and this is called a dynamic process. So once it reaches equilibrium, it does not stop. Okay. Same thing. This is really important. That's why it's written like 5 times. Okay. Next thing you talked about is Le Chatelier's principle, which says that if a system at equilibrium is subjected to stress, the system will shift in a way to relieve that stress. So some examples here that you probably saw, if we look at the Haber-Bosch process, which is making ammonia out of nitrogen and hydrogen, this is a very important reaction that uses about 1% globally of the world's money. So very costly, very important. We need it to make fertilizer. Some things that you could do to create a stress, you could add nitrogen. Nitrogen is a product, or is a reactant. So if you increase the amount of nitrogen, the reaction is going to shift to the right, and we are going to increase the amount of the product. This is because the forward rate is going to increase because we have added more nitrogen, and the forward rate depends on the concentration of nitrogen. Another way to think about this is that if there's too much nitrogen, we need to use some of it to re-establish equilibrium. Addition of ammonia is going to do the opposite. Now we are increasing the reactant. We will now have too much ammonia, so the reaction needs to shift to the left to use up some of the ammonia. Another way to think of this with kinetics is that if we increase the amount of ammonia, we are also going to increase the rate of the reverse reaction. And then removing ammonia is the opposite of adding ammonia. Temperature, I don't like the idea that heat is a product or a reactant. That is not true. But it's helpful to think about heat as a product or a reactant to come up with the correct answer here. If you have an exothermic reaction, so a reaction that is releasing heat, increasing temperature is going to cause the reaction to shift to the left. And the way that you can think about this is that you need to use heat to break apart the ammonia into nitrogen and hydrogen. So if you have more heat, you are going to use that heat to make more nitrogen and hydrogen. The opposite would also be true. So if you decreased the temperature, you need to reestablish equilibrium. So you're going to create heat, make more ammonia through this reaction. And due to that, the reaction will shift to the right. Endothermic reactions are the opposite. So if we took our reaction up here, we flip it around, maybe we balance it, that's probably a good idea. Now heat is going to have the opposite effect because we flipped our reaction. So if we increase the temperature, we would say that this reaction is going to shift to the right, and we are going to use the heat to make more nitrogen and hydrogen, which is exactly what we said up here. It's just the shift is now to the right instead of to the left because we flipped our reaction around. Same thing, decreasing temperature, we are still going to make more ammonia, but now we would call this a shift to the left, not a shift to the right, because ammonia is on the left-hand side instead of the right-hand side. Okay, pressure we will talk about more in class because this one is a little bit confusing. The system is going to shift to the side with the lowest number of particles of gas. So this is all about gases. We assume that solids and liquids are not compressible, so pressure doesn't really affect them. So if we look here, we have 4 moles of gas on the left-hand side. We have 2 moles of gas on the right-hand side. So we have more moles, aka more particles of gas on the left. A particle is the same thing as a molecule in this case. All right, so if we increase pressure to relieve that stress, the reaction is going to shift to the side with fewer moles of gas because that will drop the pressure back down. The side with fewer moles of gas is the right-hand side, so the reaction will shift to the right and we will make more ammonia. Decreased volume is the same idea as an increase in pressure. When you decrease the volume, you are essentially increasing the partial pressure of each of the compounds. So the reaction is going to shift to release the increase in pressure that's seen. And so again, it's going to shift to the right-hand side to make more ammonia. Decreasing pressure is the opposite of increasing pressure. So in this case, if we drop the pressure, the reaction is going to shift to increase the pressure to relieve that stress. And so in that case, we would make more nitrogen and hydrogen. And here's an example. So if you count the number of particles here, there are 1, 2, 3, 4, 5, 6, 7 nitrogens. If we compress the volume, now we have 2, 3, 4, 5, 6, 7. So this is like immediately we compress the volume, and then if we look at the change afterwards, we have 1, 2, 3, 4, 5, 6 nitrogens. And so decreasing the volume made more ammonia. You might see a problem like this on the AP. This is not asking you to quantitatively figure out the numbers. It's asking you to just draw fewer nitrogen molecules here than you have here. How many fewer does not matter, just a smaller number than 6. Also, you would want to make sure that if this was a problem, your stoichiometry matched up. So what I mean is that if you consume 1 nitrogen, then based off of the balanced reaction, you also have to consume 3 hydrogens. One, 2, 3, 4 to 1. So we lost 3 hydrogens. All right, catalysts confuse people. Catalysts do not shift the equilibrium. They just increase the rate at which the system reaches equilibrium. So if you see a picture like this, this is your rate of the reaction versus time. Eventually, the rate is going to become equal for the forward and the reverse reaction. And if you don't have a catalyst, it's going to take, I don't know, let's say an hour to reach equilibrium. But if you add a catalyst, that's what this dashed line is showing here. So this is with the catalyst. Now your rates are leveling off much faster. But once you reach equilibrium, it's the same forward and reverse rate reaction. Next, you can set up equilibrium expressions. These you are allowed to use your molar coefficients. These are products over reactants, and you raise your exponents to the molar coefficient. So the NH3 squared comes from the 2 in front of NH3. The 3 comes from the 3 in front of hydrogen. K is also equal to we'll do that in a minute. Okay, so this shows the extent to which the reactants form products. If you have a big K, you are going to make a lot of products. If you have a small K, you are going to have a small amount of products and a large amount of reactants. Equilibrium constant is a constant. It does not change with it does not change with concentration, pressure, catalysts, etc. The only way you can change equilibrium constant is to change your temperature. All right, so KEQ, kind of what I said on the other side, is products over reactants. So a large KEQ indicates products are favored. Small KEQ indicates reactants are favored. If the KEQ is equal to 1, which is very rare, there are a lot of other numbers besides 1, that would mean that the concentration of the reactants is equal to the products. Okay, so the way that this comes from the equilibrium expression is the equilibrium expression is really defined as the forward rate divided by the reverse rate. So this is the definition. We can write a rate law for the forward reaction, which depends on A, and the reverse reaction, which depends on B. And then we can rearrange, divide both sections by, divide by reverse reaction, and then also divide by A. And then we end up with this expression here. KEQ is also called KC if it's with concentrations in molarity. You can read all of this. Here are some expressions. We are setting up KEQ. We're putting the number equal hypothetically to the concentration of products over reactants raised to their molar coefficients. Something important to remember is that liquids and solids are not included. This is because their concentrations are basically constant, so we don't need to think about them. Okay, so oftentimes you are not at equilibrium and you want to know which way the reaction is going to proceed to reach equilibrium, and we use something called the reaction quotient Q to predict that. So for instance, here's ammonia production, and let's say we're told that KEQ is 0.105. Here's my expression for KEQ, but we're not at equilibrium yet. So I'm going to, instead of calling this KEQ, I'm going to call this Q, but I'm going to solve it exactly the same way. So I'm going to use concentration of ammonia squared, concentration of nitrogen, concentration of hydrogen. If your volume is not equal to 1 liter, make sure you're using molarity, not moles, and you get 1/2. I know that we're not at equilibrium because if we were at equilibrium, the value we would get is 0.105. So what I know is that Q right now is bigger than K, and so we have to decrease Q so that it reaches K. Well, we don't have to, but that's what the system is going to do. So for Q to drop down to be the same as K, we either need to lower the products and or increase the concentration of the reactants. So what that means is the reaction is going to proceed left, and we are going to make more reactants and fewer products. This is something you shouldn't memorize. This is something you should be able to think through, knowing that Q is equal to products over reactants, and knowing that Q is eventually going to equal K. So opposite, if Q is bigger than KEQ, if Q is smaller than KEQ, then we would either need to increase the products or decrease the reactants, which means we would need to shift our reaction to the right. Our reaction would proceed to the right. Okay, so here's another example. You plug in your off equilibrium concentrations You make sure to take care of the volume. Again, it actually doesn't matter in this problem, but I will give you problems where it does matter. We get Q is equal to 66.7, which is bigger than K. What that means is that Q is going to get smaller as it reaches equilibrium, which means we are going to drop the concentration of our products and increase the concentration of our reactants, which means our reaction is going to proceed to the left. Here's an example where you are solving for K. We know that we are at equilibrium, which means if we plug in our concentrations, we will get K instead of Q. We use Rice tables here, reaction, initial, change, equilibrium. You write out your initial concentrations. It's easier to use concentration than moles, so that's a good habit to get into. We know that these are all related with a 1, which means that the amount of CO and H2O that is used is going to be equal to the amount of CO2 and H2 that is produced. That means at equilibrium, our concentrations are going to be 1 minus X, 0.8 minus X, and X. We are then told that the concentration of hydrogen gas is 0.4 moles per liter, which means X is equal to 0.4. 1 minus 0.4 gives me 0.6, and 0.8 minus 0.4 gives me 0.4. So I'm now going to plug in all of my equilibrium concentrations and then solve for K. Here's another example. We set it up. In this case, we're using 2 moles of SO2 for every 1 mole of oxygen, which is why there's a minus 2X and a minus X. And then we're creating 2 moles of SO3, so it's going to be plus 2X. Here we're told that at equilibrium, 0.03 moles of sulfur dioxide remain. Which means this expression here is equal to 0.03. So I want to solve for X because I need to plug that in over here. So what I'm going to do is I'm going to say my equilibrium change, 0.2 minus 2X is going to be equal to 0.03, which means X has to equal 0.085. I can then use that to find the equilibrium concentrations of oxygen and SO3. I'll then plug them all in, end up with my value. Our goal in general is not to solve the quadratic equation. So if we look at number 9 and number 10, what's really nice about this is that once you set up your equilibrium expression, both the numerator and the denominator are being squared, which means you can just take the square root of both sides to get rid of the quadratic. Also in 10, you want to make sure that you're solving for what the question is asking. So in the question, it asks what is the concentration of HI, which ends up being 2X, which means that you need to take whatever value of X you have and multiply it by 2. And then sometimes our equilibrium constant is going to be so small that we can assume the concentration of A and the concentration of B are barely changing because we're going to make such a little amount of the product. And so what we can do is then we can set up our equilibrium value and we can say, okay, well, A is still going to be basically 0.5. B is still going to be basically 0.4. All that we really care about is how much C is being made. Really important, I see this a couple times, do not set X equal to 0 for C. Then you will get 0 and nothing will change. You should have an answer to this problem and you need to end up with a number. So in this case, when you solve for X, you do not want it to be 0, but we should get something very close to 0 because very little product is being made. And I ended up getting 1 times 10 to the negative 9 molarity, which is the concentration of C. Usually this is a good assumption if your equilibrium constant is about 1,000 times smaller than your starting concentrations. If you're ever wondering, did you make the right assumption, you can always take your value for X, plug it into the initial ICE table, and make sure that you get a value that's about 1 times 10 to the negative 8. If your equilibrium table gets you something very different than this number, then this was a bad assumption.